red nova remnants. So a bit of an outsider in this conference. But what I want to talk about is the possibility of trying to identify merger remnants, red novae, at late evolutionary times among the planetary nebula class. So I've talked to a few people already, and it seems like people seem to know a bit about red novae, but I'm going to do a quick introduction first. The essential thing to these sources is that they are bright infrared transients that are believed to be caused by non-compact stellar mergers. So typically we're talking about main sequence RGB stars. Sometimes we have young stellar objects involved as well. And in one source, we have a white dwarf. And the key thing to take away from this slide is that they are very, very difficult to identify at later times from what we've seen so far. We typically identify them from the eruption light curves that's associated with the merger event. So we've got multiple peaks. We have low effective temperatures immediately after the merger, down to about 2000 to 3000 Kelvin. This leads to a lot of molecules and dust being formed, hence the term red nova. And the other thing is that these sources, a bit like planetary nebulae, have quite varied morphologies. We have a much smaller sample size. This is every galactic red nova that we know about. But already you can see that, for example, with V838 Mon and Ogle 2002 BLG 360, we have these dusty shells involved. But in V838 Mon, we do also see disks and some form of bipolar jets as well. And then we've got, for example, ZK Vol and V1309 dominated by these bipolar structures. So why am I talking about red novae at a Planetary Nebula conference? Like I've said, we're trying to work out ways of identifying these sources at later times. So in terms of the link with planetary nebulae, we have varied morphologies. We have a strong role from binary interactions. We have an abundance of molecules, and quite often there's an overlap in the molecules being seen between red novae and planetary nebulae, dominated by emission lines. Forbidden, we see low ionization lines in red novae as well. And the other thing is that red novae are commonly misidentified from the onset. So V838 Mon was first identified as a slow nova. CK Vol was believed to be a planetary nebula right up until effectively the millennium. So the question that I'm kind of posing, this talk is more opening a question rather than giving answers, I'm sorry. But are there merger remnants hiding within planetary nebulae? So I've got half an answer. It's unlikely for old planetary nebulae, partly because so this is CK Vol as an example, and we see in H alpha this faint extended bipolar like hourglass nebula. So CK Vol erupted in 1670. So this is approximately 350 years old, and we still see the extended nebula. But we believe this will fade easily within 1,000 years. So obviously with planetary nebulae, we get much older ages. But for like pre-planetary nebulae, young planetary nebulae, could there be some further misidentifications that are going on? So to try and resolve this, we want to look at one particular object that I know a couple of people in the audience will recognize Denise Stavros have worked on, and this is PMK 447. So as you can see from this image from Denise's paper in 2004, it's quite a compact planetary nebula. It's not the most complex morphology. It's effectively this compact core with these two knots, lobes, bullets, whatever term you want to use, that are moving diametrically opposite. And the key thing is that, and this relates a little bit to the low ionization structure conversation that we had yesterday, both these sources are believed to be low ionization structures, and they seem to be shock dominated. And in the literature, there is an expansion velocity being estimated for about 100 to 300 kilometers per second. But this isn't why we're interested in this source. The reason we're interested is due to the chemistry. So there was a paper by Schmidt, who's a member of Lucy Sioris's team back in 2018. There was a Nature paper that examined the chemistry of this source, and they found quite a heavy, quite a strong isotopic enrichment of 13C, 15N, and 17O. And I hope it's able to see quite clearly. You can actually see that K447 is more enriched relative to typical, like classical novae, than CK Vol is. So all the authors did was just, again, raise the question, does it have a similar origin? It's interesting to say that CK Vol is the only known red nova that involved a white dwarf as the progenitor. So it's a white dwarf and red giant progenitor. This, I know, I saw that from Albert, but this was published by Romer Talenda only last year, who he was very sure that this was the progenitor. We know that it was a white dwarf and a non-compact star progenitor of some kind. So we collected I'm going to go with this slide first, slightly out of order, sorry. So we collected data from the Nordic Optical Telescope using the ALFOSC instrument. We had SMA observations already that were kind of sitting, waiting to be worked on. And then we went through the archive to look for some VLA observations. So on the left, we've got the optical emission. So we see the N2, O3, and S2 emission on top of the H alpha image. The O3 seems to be concentrated primarily in the core. The S2 emission seems to be only in the lobes, and the N2 is across the entire nebula. Nothing surprising there. But we also, from our SMA observations, detected two lines that were strong enough to detect this quite nice velocity gradient along approximately the same PA as we see for the lobes in the optical. And unfortunately, I'm not showing that image, but this kind of high redshifted lobe in the CO emission is just about starting to overlap with the northern lobe. I can show this image later on to those who are interested. But yeah, so we've got these quite strong emission maps. And the key thing from this is, so this is from Tomasz Kaminski's paper on CK Vol, where he did a SMA survey of all the lines. And so this is this is not SMA, this is ALMA, hence the more resolved structures, but the structure is there. And that's where we've got a similarity in the molecular environment we've seen for the first time as well. This previous slide, there it is. This is just to reiterate this isotopic enrichment I've already talked about. So we're seeing H13CN, very strong line, as we saw from the moment map. H13CO+, HN13C as well, we're seeing quite strong detections for those kind of molecules. So let me go through. And just an aside here, so this, so as well as all of this, we looked through the GALEX archive, and basically we've got this star here in the magenta circle. So this is a field star that we were able to cross-match with some of the optical images that we have of K447. The green circle is the 20 arcsecond radius centered on K447, and there's nothing there, which is shouting either we've got a cool white dwarf or we've got quite strong dust obscuration. Either way, there's something actually to look at there. So this is just a little bit of a summary about the results of K447. This is an ongoing work. It's not published yet. I can get more into the numbers during discussions later on. But one thing we did find, we did manage to actually constrain the effective temperature of the white dwarf. I know there was work in the past that estimated a white dwarf temperature of about 115 to 130 kilokelvin. We found that it was actually somewhat cooler than that. So this was using the Samstra method. CK Vol, this is a very, this is almost like an assumed limit. Okay, this is not very well constrained for CK Vol at all, so I only take this with a pinch of salt, but for comparison purposes, it's there. The ages are somewhat similar, of the same order of magnitude. One thing I need to also make clear, I talked about this extended nebula for CK Vol. We did look for this in K447, and we didn't find it. Now, we had the talk yesterday about more observations. I would argue more observations are therefore needed. Sorry, Ursula. But yeah, in that case, yeah. But so certainly we saw from the morphology, both exhibit the collimated jets. Like I said, K447 does not have the extended nebula. Both definitely have a strong shock interactions that are really playing a role in, I wouldn't say the sculpting, but certainly the evolution of the sources. Both have shown this isotopic enrichment. And this last thing, this is the only other bit of numbers I'll go into. In terms of the expansion velocity, CK-Vol, the molecular and the atomic environment match pretty well, approximately 300 kilometers per second. Interestingly, in K447, the atomic the atomic emission. So this is the lobes that I talked about. We had observations over multiple epochs actually, between 1997 and 2024. So we tried to estimate some kind of expansion, and we got a conservative estimate of about 300 kilometers per second, really nicely matching the CK-Vol. The molecular environment, not so much. I can maybe go back to the molecular emission maps, and you can see from the velocity gradient, it's a much slower expansion velocity, approximately about 50 kilometers per second. So this actually raised some questions in my mind about how the molecular environment was formed, whether it was a part of the outflow that produced these bullets, or whether it was pre-existing material that was perturbed. And that's one of the ones I don't have an answer for. But one thing we were thinking about is, okay, K447, there's not enough here to answer the question I was asking at the start about, could it be identified as a red nova from these observations alone? There's not enough. But one question that was raised is that with the similarity of the morphology, the collimated jets, not so much the chemistry, but certainly the kinematics, could K447 be a carbon-rich analogy to water fountains? So this is, again, not something this is something we're trying to look into as an initial phase, because obviously we know water fountains exist. We know the point of the evolutionary phase they're related to, quite a short time scale, oxygen rich. But what about the carbon rich stars? Would they go through a similar evolutionary phase, and what would that look like? So this is like an alternative scenario that we're actually also looking towards. So I think I've got a little bit of time. So just to reiterate, this is just one example I can give of how red novae are very difficult to identify at these later times. We've got all this data, lots of stuff coming in, and yet it's looking pretty similar to what we've seen for both red novae and planetary nebulae, and there's no real smoking gun that we can find yet. But it is still being considered as a candidate, and basically I want to open up that discussion to more people. I want to hear what people are saying about what we could do in the future to identify this in a better time. And shameless self-plug at the end, also looking for postdocs right now. So thank you very much.
Thanks for a very interesting talk. Just a very quick question. The expansion velocities, did you correct? How did you determine the expansion?
So there's an inclination estimate in the literature of 65 to 70 degrees that had already been found by, I can't remember if it was Udinese or if it was Romano who made that. It might have been Romano who made this estimate back in 2000. We use that as a basis.
Please.
Very nice stuff. So CK-Vol, the images you have look like a lot of these S shapes. Are you seeing precession in the system?
So you're talking about these images, right?
Yeah.
Not from my knowledge. So because obviously this is quite an old nebula, and there was a lot of SMA observations taken in the late 2010s. As far as I'm aware, they didn't find any. But
so the 2010 observations look very different from these, is what you're saying.
Sorry?
The 2010 observations?
No, these were taken in 2018, 2019 observations. So there's a series of papers with Tomasz Kamiński as the first author, talking about the molecular environment of CK-Vol. I don't know, Albert, if you can kind of give a little bit more information on that, but
Okay.
sorry to throw you under the bus there.
Sorry, I'm not a student and a postdoc. Not a student. I'm not as young as Noah. In the precession in CK-Vol, that evidence comes from the different axes of the different components. So if you look at the outflow that is now 2 arc minutes across, that is a different angle from the molecular flow. And that is a different angle from a very small accretion disk we seem to be seeing in the radio. And so that is the evidence for the accretion. When the accretion of the precession, when that occurred, we don't know. But clearly there is some multiple interactions going on. The CK Vol, by the way, is velocity up to 2000 kilometers per second, not just 300. That's
So
not
this
the
was-
high
so-
frequency.
Okay, maybe I need to check my numbers there. So that was what I found from one of Tomic's papers on the molecular environment
Now
only.
look at the paper from Banerjee. It's actually based
Okay.
on Martin Hajduk's original data. He
Okay.
got the inclination wrong. But the three projected velocities are up to 2000.
Okay, sorry about
I'll take one question, if there's anybody else. So, the connection to water fountains is fantastic.
that. Yeah,
Extremely red objects in yellow sea, which are, I think, carbon counterparts. And possibly all kind of highly embedded,
yeah,
just post-infraction, whatever happened. So I totally applaud your
yeah,
connection.
yes. This was something that me and Tomic talked about because we've got the similar morphologies, and like I talked about from the Galax non-detection, this is always sort of a typical planetary nebula, and yet we're not seeing the central star. We only estimate the effective temperature from the spectrum of the core.
And the very quick questions, so we haven't seen any luminous red novae where we can tell the binary has survived.
No,
Or anything that maybe is a bit later and maybe
No.
the dust is, so do you have any comments on, we really need to see those because we see them later on in their life.
yeah. The problem with that is that we've only got one object where we actually see the binary before the merger, like explicitly. So this is B39 scope. So that's the object where we saw the in spiral phase. We don't see that with any other source. So not seeing the binary beforehand, before you've got all of the circumstellar environment forming, I don't know how easy it's going to be to find it afterwards,
Yeah,
unless you go to much later times like CK full age.
and then you don't know if
when
it's
everything-
NLR.
and then, yeah, exactly.
One more question, Roberto, and then we'll. Jesus Stomach, where is he?
Just a quick question, did you model the SED to estimate the amount of dust?
I think that's going to be a next step. We've only just extracted the SED from CDS. We're trying to decide exactly how we're going to approach that,
So
because
that
we
would be
did
very
SED analysis of red novae before. Limited success, I'm going to say.
But, thanks Tom again.
Happy birthday, episode.
Why?
It's like
In Mexico, they call Jesus, which I don't like, by the way. So don't start calling me to.
I know.
Okay. Welcome to Accretion 101. So for those who don't know me, I'm Jesus Soala. I'm usually nor a theoretician, not an observer. So just to confuse people, and I jump between one and the other one. I want to thank the organizers for this surprise and for organizing this meeting, which I've been enjoying very much. So I won't try to convince you, because I will assume that you know that accretion is fundamental in order to understand a lot of processes or physical phenomena in astrophysics. From very fundamental things like jets, bipolar outflows, the binary evolution channel, and then you can include whatever object you like here, or whatever phenomena you want to put here. In general, what we have is a mass donor star, and then something that is accreting. We can have an accretion disk, jets, and a lot of fun things. There are different types of accretion channels, which I won't address. We have the Roche-Lobe overflow, the common envelope, which we will be hearing today. And then I will talk about the wind accretion, which is the most simple scenario of accretion in binaries. I won't address, I don't know if you can see, the wind Roche-Lobe overflow. Next talk will be about that. So you can keep your questions to that talk, or you can, if we have some time at the end, I can answer some of your questions. But okay, so the simple scenario is that defined by Bondi-Hall-Littleton accretion, where a particle moving supersonically towards the right encounters twin, and then you can define an accretion cylinder, and then each particle that crosses this effective area will be accreted by this point particle. This is the main definition. And then if this particle is moving within the wind of a companion, so the companion has this mass loss rate defined by this. This is the very easy continuity equation. And then we can define a mass accretion efficiency as the accreted material over the mass loss rate from the mass donor star. And this I will call eta BHL. For decades, this methodology has been applied to high mass X-ray binaries, and it's been working perfect. So the first people to apply this method to a binary were Davison and Ostreicher, and they used it to explain, I don't know which object, but it was a high mass X-ray binary where a neutron star accretes this material from a hot star, a companion. The winds from massive stars, they have about 1,000 kilometers per second, and the orbital velocity is about 100. So I will define this dimensionless parameter, which I will call W, and this is more or less the value for high mass X-ray binaries. The problem is that for slow winds, the Bondi-Heulier-Titov model is known to not be perfect. And in some cases, some configurations, the model parameters overpredict efficiencies values larger than 1, which is physically cannot be possible. This is another way to write this efficiency parameter, which is, I don't know if you can see it through the computer, but it's Q is a dimensionless mass ratio, is W, and this is the orbital velocity. So you can tell there are two regimes. For W values larger than 1, there's this behavior. And for W values below 1, this different behavior. Do you want me to? Okay, so this is different Q configurations. Because people have known this problem for decades, they just add an efficiency value to the parameter to the efficiency, and they just pick whatever value they want. There's no justification; it's just arbitrary. And some people just select 0.5, 0.75, 0.8. You can find a lot of papers in the literature. They just use whatever they need to fix in order to compare the Bondi-Heulier-Titov model to compare with their simulations. The list is very large. I just selected these papers. But the thing is that if you do this, although you will fix the problem for W values below 1, you will lose the best prediction for high mass X-ray binaries. And people do this, and they include these recipes into population synthesis calculations. So in order to get one good, you lose the other prediction. So this cannot be done. My opinion is that it needs to be improved. And particularly for symbiotic binaries, where we have a void dwarf accreting from a red giant star or an AGB star, these values, the velocity from the wind is about 10 kilometers per second. The orbital velocity is something about 30. So W is below 1. So all simulations trying to study the accretion in symbiotic binaries fall into the Bondi-Heulier-Titov problem. And of course, I recently jumped into the symbiotic, studying symbiotic stars in X-rays. And we need to understand the accretion in order to understand even the X-ray properties or jet launching or nebulae formation in these systems. This is our query. We will hear about this in the later talks. This is optical and X-ray comparison. So you see that jet is actually powering these extremely large hot bubbles, and this is just a toy model for the jet launching. Okay, so again, also from decades, people noticed that for small W values, the predictions from simulations, they tend to flatten. This is the way, and this is the Bondi-Heulier-Titov prediction. In 2019, these people made a lot of simulations, and they suggested that this should be taken as limits flat limits for small W values. So what we did is just include a cosine into the equation, because arguing that the accretion cylinder has to be evolving around the orbit of the, when the accretor moves around the mass donor star, the accretion cylinder has to be changing its position within the orbit. So this is actually only adding this cosine, which is defined between the these vectors. So you can identify here, this is the orbital velocity, the actual wind velocity that the accretor sees, and this is just a component of perpendicular of the accretion cylinder. If you do this, this is the new equation. It's very similar. This is the comparison between the two. And plotting the new recipe, this is just a correction with the cosine. These are the solid lines here. So for large W values, we recover the von Littleton accretion recipes. But for small W values, we have this flattening predicted by the simulations. These are, again, very low. You may not see them, but Q is the dimensionless mass ratio, and W is the dimensionless velocity ratio. For small W's, the function limit is the limit is about the Q square, and this is the typical Bondi Hole. Okay, so now this is our prediction, and all of these points are simulations from Nagai 2004. They did it for different conditions in the wind and in the physics in the simulations. So our analytical prediction is way better than the Bondi Hole Littleton accretion, specifically for values below 1. And this is the Saladino simulations compared with the solid lines are our predictions, and the dashed lines are the standard Bondi Hole prediction. This is getting better. So now we can start comparing different systems, accreting systems. In this figure, I am showing you in dashed lines contours of the accretion efficiency. And then this is the W and Q parameter space. And then you can see that high mass X-ray binaries are less efficient accreting than symbiotic systems, for example. And this, you can ask me about it. I won't go into the details, but this is a non-valid region of our model. So we started applying our formulation into evolving systems. This is particularly for evolving symbiotic systems where we have stellar stars with 1, 2, and 3 solar masses evolving from the red giant branch into the AGB. And we can see that we do numerical simulations, and then we see that the stars or the systems evolve from the flattened part of the equation into the higher W values when the winds from the AGB, the pulsating AGB, start increasing. So we see that the systems evolve from one region into another one. For these specific cases, these are extended orbit systems. Next talk will be about the compact orbit systems. And this is just the same system, but adopting the two different recipes. So you can tell the difference is large. So we actually just limit to 1 the efficiency here. But this difference will give us different predictions for the supernova explosions in population synthesis calculations. So I'm sorry for all the people who did these calculations before, but you need to revise these calculations if you modified your accretion recipe by just adding one arbitrary parameter. And of course, we can extend the calculations for eccentric cases. The equation becomes more complex because now it depends on eccentricity, the wind velocity profile that you adopt for the calculation. This is just examples or how fixing the rest of the parameters and then changing eccentricity, how the efficiency changes, changing the W value or the beta law of the wind, of the free streaming wind from the mass on the star. So depending on which parameter you want to play with, you have more or less different configurations of the mass accretion history. And our calculations are plainly analytical, so we try to compare with simulations and the dashed line is the Bondi hole, the standard Bondi hole. The solid blue line is our prediction, and the red dotted line is from this simulation. So we can recover the mass accretion history more or less, or the average or the median, if you like. But that this, which we don't have, processes differently the accretion. So this is something that we still have to deal with. We can compare with, these are observations from our query in X-rays, from Chandra and Maximum Newton. These are different predictions from our simplistic analytical model. So we can more or less say something about the evolution. And these are observations during periastron passage. So we can more or less reproduce for different parameters. And finally, so what we are doing right now is we are running a family of simulations in order to confirm that we are predicting is realistic. So this is just an example that one of these simulations, because we don't care about the outer nebula. Our simulations, you can tell, they're very short boxes, small boxes. Different diamond and bullet symbols are simulations, and then the dashed lines are predictions from our model, and this is the Bondi hole. You can tell we are recovering from the analytical calculations what we see in the simulations. And this is something that is very specific, that in order to, if you want to use the model, and we still don't know how to make an observational prediction, but it is, the accretor does not see the unperturbed wind. It sees a modification because of the potential of the two stars. So this is something that you need to include in order to make these kind of plots. So I will leave you with my final remarks, which is we perform a geometrical calculation on the Bondi hole Lyttelton accretion process, which impacts the small wind regime. But we recover the large wind, the fast stellar winds regime for high mass X-ray binaries. Binary evolution and population synthesis, they need to be revised if you want to make better predictions for supernova explosions, and you can keep reading them.
Questions?
Have you attempted to, you just showed that you did the simulations and they agreed quite well with the new model, but have you attempted to do simulations for the eccentric cases yet?
We do have them. Actually, the R query system is a 0.45 eccentricity. So this is one example.
Hi, Jesus. Thank you for your nice talk. In high mass X-ray binaries, they have the so-called Corbett diagram, which relates the period orbital period and the spin period of the neutron star. And the wind accretors are separated in this diagram of the Ocelot accretors. So I'm wondering whether in your model or in this kind of models, there is some observable which can be related with the spin period of the star.
Not yet. Oh, sorry.
No, I was meaning something like, for example, in Arrow Party, it has a jet, so maybe it can be related with the rotation in the jet.
Yeah, so not yet, because our analytical model currently does not include any calculations of angular momentum or disk formation, nothing of this. And next up, we'll be addressing simulations, and we'll stop whenever Roche-Lobe overflow is reached by the system, because it requires more hydrodynamic simulation. So we cannot do that only by analytical calculations.
Hi, Jesus. Thank you. Beautiful. I like analytic models, so this is beautiful. Can you explain again the reason, the geometrical reason behind the cosine?
So when people apply the Bondi hole Lyttelton they don't correct the orientation of the accretion cylinder they just assume that it's accreting the wind, and it sees the wind from the star. So this is the main usage that people use for high mass X-ray binaries. But here the accretion cylinder, if this is an eccentric case, because it's way better to see it like this. So the accretion cylinder is the velocity that enters this area is not specifically the radial velocity.
The composition of the two velocities.
Yes, it's just vector analysis, so it's actually.
It used to be called a sort of aberration, right?
Sorry, again?
Did it used to be called aberration? Isn't it
I
aberration?
don't know.
I don't know that's
Yeah.
maybe.
This is line of the.
Yeah.
I have a quick question if there's not. So first of all, you said something, you said, now we look at the model, at the SPH model, which gives you the truth. That's not true, okay? So
Well-
both the model and the analytics are equally wrong. So, but one more important thing, how do you measure? Because from the model, you're gonna have to measure that
Yeah.
quantity to compare, and that measurement is very tricky.
Right now, we're measuring 5 degrees before the equator arrives, right now. But we are trying to come up with an analytical estimation, because we need to give something to observers. So this is something we are still thinking about.
Any more questions? If not, let's thank Jesus again.
Okay, thank you. I thank the organizers for letting me here to talk about our recent study that, as Jesus taught us previously, we are now studying symbiotic binaries by n-body simulations and how do they accrete, but now in the compact regime, and invoking an accretion mechanism that is called the Wien-Roch log overflow. As we know, a symbiotic system is composed by a primary, which is mainly in the RGB direct giant branch or asymptotic giant branch phase, and is losing mass through wind, slow and dense wind, and it is orbited by a compact accretor, and this, that mainly it's a white dwarf, is accreting the wind. As Jesus has already given us a great introduction of the accretion mechanisms of von der Littleton and the new modified accretion model, the accretion efficiency can be expressed by two-dimensional quantities, which is the mass ratio and the velocity ratio. So, as we know, symbiotic binaries have velocities ratio that are in the values below 1. So as we have seen previously, now when we have performed simulations comparing the different accretion model schemes, we have seen that now the classical von der Waals that over predicts the accretion efficiency, now it is well has values. And of course, if we see the velocity ratios larger than 1, we are having similar orders of accretion efficiency. So this work has been already published, and we explore different configurations of orbital distances and different stellar masses and masses of white dwarfs. So, what's next? Here, I present you what is called the Wien-Roch log overflow that has been proposed by Mohammed and Podsiadlowski in 2007. And what they say is that in order to have these accretion mechanisms, two conditions should be met. The first condition is that the wind velocity should be shorter or comparable to the orbital velocity. And the second one is that the injection radius of the wind, which is mainly assumed as the condensation radius of dust, is larger than the Roch log radius of the system, of the primary star. So when these conditions are met, the wind is confined, gravitationally confined, and redirected to the white dwarf by the Lagrange point L1. If, in the other hand, if we have the condition radius shorter than the Roche-Lobe radius, so the wind can expand and there is no redirection through the L1 Lagrange point. So, as we say, the first step was to compare the different accretion mechanisms, and now we want to explore how the new accretion model affects the orbital evolution of symbiotic binaries, plus adding extra physics, such as wind drag and tidal forces. And we want to answer this question. How do all these effects, wind accretion, wind overflow, wind drag, tides together shape the orbital evolution and also the accretion efficiency of compact binary systems? So how do we do this? First, we use the N-body packages available publicly, Rebound plus the extension that add extra physics, Rebound X. And we use stellar evolution models that have 1, 2, and 3 solar masses. Here in these plots, I showed you the HR diagram, and in color is highlighted the stellar phase, evolutionary phases that includes the red giant branch and asymptotic giant branch that we are modeling. Here we see how the evolution of the mass loss ratio is during the RGB and then the thermally pulsating AGB phases, that when we show the details, we can clearly see how the thermal pulses are drawn. We perform 3 types of simulation. We call the first type of simulation Sim-A, which includes only wind accretion. So when the white dwarf is orbiting the primary, we perform the accretion efficiency as the modified accretion Volnikov-Littleton model. But when the condition that the condensation radius of dust is larger than the Roche-Lobe radius, then we use this new accretion efficiency recipe that has been proposed by Abad and collaborators, that primarily they parametricize the hydrodynamical simulations that Mohammed and Posiadowski performed in the original paper to put in terms of the mass ratio and the ratio of the condensation radius and the Roche-Lobe radius. This efficiency is capped to 0.5 because in those hydrodynamical simulations, no efficiencies larger than 0.5 were achieved. So that's why they use as a maximum accretion efficiency. The next type of simulations are including the wind accretion plus wind drag force. In this case, we define the drag force as here, as you can see, that is the accretion rate times the relative velocity. Here, you see that, for example, if the white dwarf is moving in this direction, it will feel a drag force that is in this direction. And finally, we are adding an extra physics that is a tidal force. To do this, we use the tidal lag model that is available in the Rebound X package that basically includes how the tidal bulge that is produced by the accretor to the star is misaligned and produce a tidal lag that can cause a torque, and it can reduce orbital energy. So the basic parameters of this model are the constant time lag parameter and the tidal lobe number, which these two are calculated at each time step of the simulation, and also it has to take into account the interior structure of the star. Here I show you the density profiles at different time scales of the stellar evolution model. For example, number 1 is the beginning of the red giant branch. Number 2 is the tip of the red giant branch. And number 3 is the maximum radius achieved during the thermally pulsating AGB phase. So we evolve the system through the red giant branch to the ending of the AGB phase. And we stop the simulation when some conditions are met. The first one is that we don't want to enter to the post-AGB, so we stop the simulation when the central star reach a temperature around 4,000 Kelvin. Also, if the accretor reach the Chandrasekhar limit, we also stop the simulation there because we do not model the supernova explosion. Or if the donor star field is Rochlov, then we stop also the simulation because this Rochlov overflow needs an hydrodynamical treatment. Here I showed you the configuration that we are exploring. The first is that we are simulating compact systems, 2, 3, 4, 5, 6, and 7 AU orbital separations. The initial donor masses are 1, 2, and 3 solar masses, and the initial accretor masses are 0.7, 1, and 1.2 solar masses, which make a total of 162 N-body simulations, 54 per scintile. Here I showed you the results that we are getting. In this graph, we show the orbital evolution of the different simulations that are highlighted in colors. Here I showed you how these first 2 simulations end to the end of the TP-AGB phase, and we see how the orbit expands due to the mass loss of the donor star. However, when we include tides, the tidal forces reverse the inward migration, and this simulation stopped because this dotted line, that is the Rochlov of the donor star, met the stellar radius. So Rochlov overflow starts here. This silver shaded region represents the condensation radius of the donor star. So when the Rochlov is shorter than this radius, so when Rochlov overflow is activated. Here is another example that even when drag force in one case has an orbital expansion, here is reversing. And these 2 simulations are stopped here because they reach the Chandrasekhar limit. But you can see that is the donor star has a high mass, and also the accretor larger than is a 1 solar mass star. So to have a better understanding when the Rochlov overflow is activated, in red, I showed you in these graphs of accretion efficiency versus time, the times where the Rochlov overflow is activated, and you can see that is in episodic times. And here are some statistics. We find that when we only have weight accretion, almost 20% of the simulations achieve the Chandrasekhar limit. However, when we start adding extra physics, we start to see that this limit is not met. But when we add all the physics, including tidal forces, none of the accretors reach the Chandrasekhar limit because almost 90% of them are stopped because they are reaching the Rochlov overflow stopping. Here we compare the final orbital distances that the simulations have been achieved, also separated by the 3 types of simulations, and in order to compare with the observed symbiotic, well-characterized symbiotic binaries that are available in the NEON-LATE database of symbiotic binaries. And as you can see, when we are adding all the physics, we are recovering the observed distribution of orbital distances. So if we want to connect with the central stars of detected binary central stars in planetary nebula, we see that all of them have periods of scales of days. Our simulations have scales of hundreds of years. But we should remember that these are stopped in the Roche log overflow when it happens. So it means that in order to get these periods, Roche log overflow should need to be modeled and also common envelope. And these are the messages that I want you to share with you, that compact symbiotic binaries alternate between the accretion schemes, and only the high mass accretors and high mass donor stars can reach the Chandrasekhar limit, and tides and drag forces should be included if we want to model a more real system. Thank you.
Good. Super Nagor, thank you. I have one question. Why you have the accretor masses from 0.7, 1.2? Why not something lower?
Well,
Because that's a higher end of the distribution of the observed masses of the white persons environments.
yes. Well, it's because we want to model systems that, for example, in order to have a symbiotic for a accretor of 0.7 means that when they both were in main sequence, this one should be larger than 5 solar masses as main sequence star. So we need a binary configuration for which the one should evolve faster, right? So that's why we choose 0.7 as the lower limit. Because if we model 1, 2, and 3 solar masses, so larger in masses in main sequence gives you a more massive white dwarf.
Sure, but then when you compare with the observed population of symbiotic white dwarfs, then in your simulation you're missing this lower end, which is actually more populated, because the median would be somewhere around 0.6, 0.7.
Okay.
And you have half of the population that you are not modeling. So it could be interesting to have that.
Okay. Yes.
Okay.
Yes.
Thank you for your talk. Your simulation starts with a white dwarf already in place, or do you completely start from main sequence binary?
Yes, we start by having the main sequence, the one star in the red giant branch phase, and the white dwarf is already formed. So that's where we start the simulation.
So tides, I would say, are like maybe the most unknown thing in astrophysics, like probably within 5 orders of magnitude or more. We don't know tides. But I'm curious about the implementation on how rebound X handles this. Does it adjust for different evolutionary states? Because one thing we do know, no matter what tidal prescription you pick, tides on main sequence phases are significantly weaker than they are when they get to the giant phases. So they go up by at least 5 orders of magnitude with the giant phases. So does it, like, I guess, interested to know more about what rebound X is doing with tides.
Okay. Well, the model that we're using and is available in Rebound X is the weak friction model, and it's equilibrium tides only. So one interesting thing is that as I showed, it depends on the interior structure of the star because they involve the tidal log number that is calculated by here. I have here. Solving this differential equation that involves the density profile. So, and the converting friction time is calculated by the stellar parameters. So, of course, here we are assuming that the bodies are not rotating, just for simplicity. However, if we include rotation, things may change because now the tidal, the lag will maybe is not behind or it will reverse. And so instead of pulling inward, the feather pulls out. So that's another thing that we should explore in the future.
Thanks.
Okay, let's think. Posters, numbers 19, 23, and 25. Let's see. 1, 2. The 9, 20.
Hello, everyone. I'm Simon. I'm a PhD student working with Jan, and I'm presenting my work on tracing fullerene-linked dust variability in the planetary nebula TC1. TC1 looks like this, and we have MIRI-MRS observations of the area in the white rectangle. Now, we're interested in TC1 because it contains fullerenes, and fullerenes only exist in a very specific kind of environment. And my research is on investigating the dust aspects of that environment. So if you look at TC1, a typical spectrum you will see is something that looks like this. And let's remove all of the contributions that we're not interested in. So first to go are the continuum and unresolved lines. And what you're left with is a bunch of strong features, most of which are the infrared bands of fullerenes. So remove those, and what you're left with is two broad features, which we call plateaus. And so we have the 6 to 9 micron plateau, and then we have the 9 to 13 micron plateau. And in TC1, these two plateaus have a very different spatial distribution. But not only that, we also see interesting spectral variations. So these are some different spectra from different locations in the nebula. And so from a combined spectral and spatial analysis, we conclude the following. The 6 to 9 micron and the 9 to 13 micron plateaus have different spatial distributions, indicating they are produced by different carriers. The spectral shape of the 6 to 9 micron plateau is constant throughout our field of view, and this indicates that it is produced by stochastically heated material. And then finally, the 9 to 13 micron plateau consists of at least 3 components, one of which we have identified as silicon carbide. Thank you.
Hi, everyone. My name is Teo Kuri, and I'm based at Chalmers University of Technology in Sweden. And this is a study that I have been doing with other people about Mira, the archetypal Mira pulsating star. And it was all triggered when we got some ARM observations, which shows a bunch of lines from molecular emission. And in 2017, we saw that a lot of the lines traced these two lobes here. There's one on the left and one on the right there. And then we got later observations in 2023, and these two lobes seem to have expanded. And then I looked in the archive of SPHERE on the VLT, which is a polarimeter, image polarimeter. And there were observations all the way back in 2015 that also traced the edges of these lobes. And you can see here the molecular emission superimposed with these lobes. So then we can see the very nice expansion of these two structures over these 80 years, and we can trace them back to have been ejected sometime 15 years ago. So this is really mass loss of HB stars in real time that we are seeing. We can get a lot of interesting information out of this. So if you're interested, you can come look at my poster and we can talk more. There's a lot of questions that come up as well. It seems to be a much more powerful event than you would expect for a star like Mira, which loses mass at a fairly low rate. So yeah, but if you're interested, I'll talk more about it. Thank you.
Okay. You're safe.
Hello everyone. I want to tell you briefly about the 3D physical structure of two board game planetary nebula, specifically Abel 30 and Abel 78. Both are composed by a disk, a diffracted disk, and bipolar outflow formed by compact knot and cometary tails. And this in this world is the very first time for a board game planetary nebula, of course, that we have velocity projected in the plane of the sky, and now data from the GTC, the IFU GTC Megara, with high spectral resolution and now spatial resolution to resolve each knot individually and calculate the velocity, the radial velocity for each knot individually. In this case, we perform Gaussian profile to the emission from the oxygen-free lines, and with both velocity, with the velocity projected in the plane of the sky and the radial velocity, we have everything all we need. We can calculate the 3D real velocity and the position of each knot individually. And now in this image, we can see the velocity against the distance, the real velocity against the distance, and the ratio, the velocity distance ratio against the distance. We can see how the expansion is homologous and how the knots are decelerating as we move toward higher distance. In this image, I show you the position of each knot, the 3D position of each knot, and this is not a model. This is not without any assumption. This is just the real 3D visualization of the inner region of each nebula, and this is haven't done before for a board game planetary nebula. This is still an ongoing work. I don't want to jump in early conclusion, but the results for the moment are being very revealing. If you have any question or that, I will be glad to resolve of them all. Thank you.
Thank you, everybody. Hold the questions for the discussions later on. Before we go for coffee, I would like to start a little practice. So we are here. We know nature does this amazing thing very well. We know that computers do it very badly, but we have another tool, and it's right here, right now, and that's brains, lots of them together. So let's take the opportunity. If you have a particular question you're interested in, particular class of objects, anytime this week, come up and say, hey, anybody interested in this? Let's meet for coffee, and then we can even have later meetings, lunch, or whatever. So I'd like to launch this. If anybody's interested in what I lovingly call Hans van Winkel objects, so post-RGB binaries discussed by Ravendra yesterday, progenies and children and parents of this class. Can you meet me a coffee now? Then we can pick a suitable time for everybody, maybe to meet in the side room. And please do this, because this week, but not next week, you have a lot of people, have a lot of knowledge right here, right now, okay? And can we go for coffee? Yes.